Match the following equations to the corresponding graph. We're at a point now where we've seen every type of cubic graph shape, or roughly the sort of different behaviors that you can get for your cubic graphs. And particularly, we've had a look at what different behaviors you can get at the x-axis, whether you have 3 x-intercepts, whether you have 2 or 1 x-axis intercept. So this question is asking us to bring together all that knowledge and try to recognize the shapes based off what we've learned so far. To do that, the best thing to look at is the behavior at the x-axis. So I'm going to go through each of these graphs and just summarize what I notice. For this first one, I notice that there are 3 x-axis intercepts. So what that tells me is that the formula must have 3 linear factors that, when it's fully factorized, will correspond to the x-intercepts, or the roots. Next, for this one, I can see only 1 x-intercept. And something else I noticed that's interesting about this graph compared to the others is that it doesn't have the minimum and maximum turning points. It only has a point of inflection. Only has a point of inflection. What that should tell you is that if it's only got a point of inflection, it must be something that can be written sort of in this form that we've seen before, x minus h cubed plus k, where the point of inflection corresponds to the h and the k. So it's got to be something that follows that form, or can at least be factorized to be written in that form. Next, we have this one, which only has 2 x-intercepts, and what's interesting about this one is that it's also a repeated root. So we have 2 intercepts and also a repeated root. Right? And the last one is this one. This one only has 1 x-intercept as well. And it has a bit of something going on down the bottom, so it might be in a slightly different form to this. Although this one also has only 1 intercept, this one only doesn't have any minimum and maximum turning point, so that might be able to help us narrow down our choices. Now let's go through the formulas and try to summarize what we see in the formulas. In this first one, I see a linear factor, and then I see a quadratic factor. And just quickly double checking that the quadratic factor can't factorize any further, I'll use the discriminant. So here I have a equals 1, b equals to minus 4, and c is equal to 5. Substituting that in, minus 4 squared is 16, minus 4 times 1 times 5. So I have 16 minus 20, which is minus 4, which is definitely less than 0. So we can confirm that this has no solutions. And since the quadratic term has no solutions there, we can safely say that this one will have only 1 x-intercept. 1 x-intercept. Now, moving on to b of x, I can see 1, 2, 3 linear factors. If I equated this to 0 and did the null factor law, I would have 3 solutions. Okay, so I can safely say that this one has 3 x-intercepts. Next, moving on to c, this one has only 1 term overall. So if I tried to equate that to 0, this would only have 1 solution. So this has only 1 x-intercept. Finally, we have d of x, which has 2 linear terms, one of which is squared. This corresponds to, if you recall with the squared, is a repeated root. And at the repeated root, the graph will just touch the x-axis. Okay, so this has 2 x-intercepts, one of which it just touches at. All right, now going through, I think there are a few that are quite obvious that we can do straight away. So there's only one which had 3 x-intercepts, which was b of x. So I can put that down as this one must be bx. There's also only one that had 2 x-intercepts, one of which was a repeated root, which is this one. So we can say that this is dx. Now it's the last two that are a bit trickier because there's only 1 intercept in both. However, in this one, we mentioned that it's got to be in this form, in the point of inflection kind of format, where we can just translate it around it doesn't have any curves. Over here, this is actually exactly in that form. We have 2x minus 0 cubed plus 0, because the point of inflection is actually located at 0, 0 in this formula. And that's exactly right. This is 0, 0. That's where our point of inflection is. So this particular one must be CX. And that leaves just AX to be the last one over here. Now, a few other things that you can do if there were more options, or if you're unsure about some of your choices here, is we can have a look at the actual values of the intercepts and just make sure they're on the correct sides of the axes. So for example, this one, if we did the null factor law really quickly for this one, we would see that the intercepts are at x equals 0, x equals 1, and x equals to minus 1. And I can see, in fact, that there is a negative 1, there is a 0, and there's a positive 1. So even though we don't have an exact scale, we can see that they're roughly equivalent to what we have in the formula here. We've already identified that the point of inflection for this one is at 0, 0, and that the intercept would be at 0 as well. Then for this one, this is quite important to check that the repeated root is actually in the correct place. So if we put this one and use the null factor law in that really quickly, we'll get that x is equal to minus 1, that's the first bracket, and then we have x is equal to plus 1, which is from the repeated root. So this one is where it's going to just touch. It's going to touch at x equals 1. And in fact, this could be x equals 1 and this could be x equals minus 1. And it's just touching at the 1, so this is also correct. Finally, we can also double check just the last one. We're expecting our x-axis intercept to be negative. So if I do the null factor law with this one, I can see that from the linear term, I will get x equals to minus 3. So this could probably be x equals minus 3, and so our shape must be correct as well. So that's how we can go through and apply our knowledge of the different shapes of the cubic graphs and just try to picture the graphs without actually sketching them.